Mock exam, January 2017. This question is about the electron configuration. Give the full electron configuration, so that means you shouldn't be using noble gas cores, of an aluminium atom and a chromium 3+ ion. So the first thing you need to do is use your periodic table to work out how many electrons each one of these has. So aluminium has 13 electrons. Now a chromium atom would have 24 electrons. So the chromium ion is going to have 21 electrons. So let's write the aluminium one out first. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p1. And then if you check the little numbers, you should see that adds up to 13. So we know we've got that one right. Right, for the chromium, just underneath the line, I'm going to write the electron configuration for the chromium atom. So we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And if you just do a quick check to make sure that does add up to 24 electrons. Now you've got to remember that the 4s shell fills first, but when ions are formed, the 4s empties first. So these are going to be the first to go, and then we're going to lose one of these. So we can write out the electron configuration of the chromium ion. So it's ending in 3d3. Remember, for all the transition metal ions, whenever an ion is formed, it's going to lose the 4s electrons first. So when you've got an ion, you shouldn't see an incomplete d subshell and 4s electrons there. Okay, we've got to deduce the formula of the ion that has the same charge, that has a charge of 2+ with the same electron configuration as krypton. So if we have a look, krypton has got 36 electrons. The ion we're looking for has lost 2 electrons. So if you count on 2 elements from strontium, from krypton, we're going to have strontium. Now it asks for the formula of the ion. So it's Sr2+, and it's important that you put the 2+ in. Make sure you copy the correct symbol from the periodic table as well. You're given a periodic table in the exam. Make sure you're using it. Deduce the formula of the compound that contains a 2+ ion and 3- ions that both have the same electron configuration as argon. Okay, so if we have a look for the 2+ one, we want to count on 2 elements after argon because it's lost 2 electrons. So we're going to have the calcium ion, and 3- will have gained 3 electrons. So that's going to be 3 before, so it's 1, 2, 3. So that's going to be the phosphorus 3- ion. We've got to make sure the charges are balanced. We've currently got a 2+ and a 3-, so I'm going to add another 2+. So I've now got 4+ in total, and only 3- over here. So I'm going to add another one of these. I've now got 6-, 4+. So if I add another one of these, those now add up to 6+. Those add up to 6-. So I know it's going to be balanced. So my formula must be Ca3, because I've got 3 of them, P2, because I've got 2 phosphoruses. These simple formulae are something that you need to be able to do. If you are still getting confused by these, you need to go right back to the beginning of the year and you need to practice those formulae. If necessary, go to one of the workshops. Any of the teachers will be happy to help you with this. This question is about period 3 of the periodic table. Deduce which of Na+ and Mg2+ is the smaller ion and explain your answer. So if we have a look at Na+, Na has 11 protons and it's only going to have 10 electrons because it's lost one to form the positive ion. Magnesium has got 12 protons and only 10 electrons. So the effect of these 12 protons on an ion that has the same number of electron shells is it's going to pull everything in, and the atomic radius, the ionic radius, is going to go down. So the one that is the smaller ion is going to be Mg2+. And the reason you need to put down for that is Mg2+ has more protons. And that will get you 1 mark. And it's got the same shielding, or you could say it has the same electron configuration. So both of those 1 mark, and then Mg2+ for the second mark. Write an equation to represent the process that occurs when the first ionisation energy for sodium is measured. So the first ionisation energy is the enthalpy change when 1 mole of atoms becomes 1 mole of positive ions in the gaseous phase. So we've got to remember it's a gas. So we're starting with a sodium atom and we must put that state symbol in. It's going to lose an electron to form a positive ion, which is still a gas, and there is the electron it's lost. You don't have to put a gaseous symbol on an electron. The first ionisation energies of some period 3 elements are shown in figure 1. Now, just before I do anything, I just want to identify what's going on. So 11, atomic number of 11 is sodium, then I've got magnesium, then I've got aluminium, silicon, phosphorus, sulfur, chlorine and argon. That just makes it a little bit easier to map on what you've learnt. So we've got S1, S2, P1, P2, P3, P4, P5 and P6. So we know there's going to be a slight increase going from sodium to magnesium because we've got an increase in nuclear charge and we've got the electrons going into the same subshell. So we're going to expect the value for magnesium to be a little bit higher, but not too high. So we're looking between 600 and 800. So I'm going to put mine about there. That way you can see the drop then between magnesium and aluminium, which you'd expect to get because you're changing subshells, and that extra little bit of shielding means that aluminium's outer electron is slightly easier to remove. Then we're going across, we've got P1, P2, P3. Remember, there are 3 p orbitals, so these electrons are in their own orbitals. When we come to put the 4th electron into the p subshell, we're going to have to start doubling them up, which means there's slight repulsion. If there's slight repulsion, it means that electron is going to be a little bit easier to remove. So we're going to expect a dip. So we're going to expect it to be slightly lower than for phosphorus. So between about 800 and 1040. So I'm going to put mine about there. So you can see there's definitely then a drop between those two, and then we've got the continued increase. It's not a huge drop though. So we've completed figure 1. Now we need to explain why the first ionisation energy of sulfur is different from that of phosphorus. So to make it a little bit easier, I'm going to write out the electron configurations, because straight away then you can see what's going on. So sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. And phosphorus is the one before. Oops. So it's got 1 less electron. So what's going on is we've got our orbitals. So if this is the 3p, so for this one, they've all got their own orbitals. For this one, the fourth one is going to have to share. So it's going to mean there's a slight drop. You've got to be able to put that into words. So the way to say it would be, in sulfur, the electrons are paired in the 3p orbital. And then the paired electrons repel. So less energy needed. And you would get one for each of those lines. You don't have to put the diagrams in, but if you're not sure of where to go with the question, it's probably worth drawing those out just so you can see what's going on. It's so much easier to put into words when you can see what's going on. And you get 1 mark each for the correct crosses on the graph as well, and that's where the 4 marks come from. This question is about a white solid MHCO3 that dissolves in water and reacts with hydrochloric acid to give a salt. A student was asked to design an experiment to determine a value for the MR of MHCO3. The student dissolved 1,464 milligrams. We're going to have to be careful here, we've got this in milligrams. To convert milligrams into grams, you divide by 1,000, so that's going to be 1.464 grams, which is what we usually use in our moles calculations. So the student dissolved 1,464 milligrams of MHCO3 in water and made this solution up to 250 centimetres cubed. So we've got a change here. Watch that one. Only 25 centimetres cubed of the sample of solutions were titrated with 0.102 moles per decimetre cubed hydrochloric acid. The results are shown in Table 1. So the first thing we've got to do is we've got to calculate the mean titra. Now remember, this is a normal titration results table. You don't use all of the results. You're looking for the concordant results. So that's 2 results that are within 0.1 of each other. We're going to ignore the rough one. And then if we look at these 3, these 2 are within 0.1 of each other. You need to indicate which ones you're using. Now you could do that by circling them on the table, or when you come to work out your average, showing what it is. Now it's really important with your calculation that it's nice and clear, because if you do make a mistake but the examiner can see what you've done, they're going to give you credit. So I'm going to write average titra. Then the examiner knows exactly what I'm doing. And I'm going to show which 2 I'm taking an average of and how I've done my average. Remember, the values were to 2 decimal places, write your answer to 2 decimal places and no more. The second bit of the question is asking me to use this to determine the amount in moles of HCl that reacted with 25 centimetres of that solution. So I'm going to work out my moles of HCl, and to do that it's going to be a vol times conc divided by 1,000. And I know my volume is my average titra. The concentration is given to us in the question, and it's 0.102. Then divide it by 1,000, because that converts the volume into decimetres cubed. And that gives us a moles of 9.89 times 10 to the minus 4. For this question, you get 1 mark for identifying the 2 concordant titras, either on the table or in your calculation. Another one for getting the correct average, and then a final one for working out the moles. Part 2, calculate the amount in moles of MHCO3 in 250 centimetres cubed of the solution. Okay, so we've worked out how much hydrochloric acid we had in 25. And we've got an equation up here. We know that they react in a 1-to-1 ratio. So the moles of HCl are going to be the same as the moles of MHCO3. So the moles of MHCO3 in 250 centimetres cubed are going to be 9.89 times 10 to the minus 4 times 10. To go between 25 and 250, it's a factor of 10, so I'm going to times this by 10. So I've done that first bit. I then need to calculate the experimental value for the MR of MHCO3 and give my answer to an appropriate number of significant figures. So the relationship is going to be moles equals mass over MR. And I'm trying to work out the MR. So this is going to be mass divided by moles. And I need to go back to the question to find out what mass was used. And our mass is here, but we've got to be a little bit careful because the mass is in milligrams. So convert the mass first into grams by dividing it by 1,000. Then we want to divide it by our moles. And that gives an MR of 148. Now you'll get an answer which has got more decimal places with your calculator. But if you have a look, all of the information you've been given in the question, the smallest number of significant figures is 3. So these are to 3. There's things up at the top that are to 3. If you have a look here, there's nothing that's less than 3 significant figures. So our final answer should be to 3 significant figures, which is what we've given it. If you've done more than that, you're going to lose a mark. So you get 1 for doing it, if you're getting the correct answer. You get a second mark here for getting everything into that equation correctly. And you get 1 mark for working out the moles in 250. The student identified use of the burette as the largest source of uncertainty in the experiment. Using the same apparatus, suggest how the procedure could be improved to reduce the percentage uncertainty in the burette. Justify your suggested improvement. So if you think about percentage error, it's the quantity used, so it's the error divided by the quantity used times 100. So if we want to reduce it, if we can increase the quantity used, then it's going to reduce the percentage error. So we need to increase the volume of acid used. Now we can't just use more acid because it only takes a certain number of moles of acid to neutralise the metal carbonate. So we've got a choice. To be able to use more acid or a larger volume of acid, we'd either have to use a larger mass of the solid, or we could reduce the concentration of the acid. If the concentration of the acid was more dilute, we'd need more of it to neutralise the metal carbonate. And the justification for that would be so you have a larger titra. Another student is required to make up a 250 centimetre cubed of an aqueous solution that contains a known mass of MHCO3. The student is provided with a sample bottle containing MHCO3. Describe the method, including apparatus and practical details that the student should use to prepare the solution. Okay, so the first thing they're going to need to know is the mass of that solid. So it's in a sample bottle, So the first thing they need to do is to weigh the sample bottle. Now they want to do that on a fairly accurate balance. So I would say using a balance of at least 2 decimal places. Okay, the next thing to do is to transfer that either into a beaker first to dissolve, but when we did this, we transferred it straight into the volumetric flask. And we want to make a 250 solution, so we want to transfer it into a 250 centimetre cubed volumetric flask. Now there might be some of that metal carbonate left in the weighing bottle. So what we'd want to do is to reweigh the empty weighing bottle. And then the mass of MHCO3 is going to equal the initial mass minus the final mass. Okay, so we've now got the metal hydrogen carbonate into the volumetric flask. We want to add a little distilled water. Taking care to rinse the funnel into the flask. And then if there are any little bits of the carbonate on the funnel, we know they're going to go in. Before we add too much water into that volumetric flask, we need to make sure all of the metal carbonate has dissolved. So swirl the flask until all the metal carbonate has dissolved. We then want to make the flask up to the mark using distilled water. And then we want to make sure that it's fully mixed. So you would invert flask with the stopper in place, obviously, about 10 times to ensure it's fully mixed. Now there's nothing to stop you drawing little diagrams as well, just to show what you mean by making it up to the mark. So it might be something like this. You can always add a little bit extra detail. Now questions like this are marked in a series. Now to be able to get between 1 and 2 marks, you have to have at least 2 stages. So the first stage is transferring and weighing the solid. The second stage is dissolving it in water. The third stage is making it up to the mark and agitating it. To get the second stage, which is 3 or 4 marks, you have to have got all of those different steps. But you might have the odd admission, it might be not quite detailed enough. To be able to get level 3, you must have every stage in. It must be written clearly and logically. Don't forget, you do have more space on the next page, so if you'd gone on to the next page, that would have been absolutely fine. Table 2 shows some data about the elements bromine and magnesium. So we've got their melting points and their boiling points. In terms of structure and bonding, explain why the melting point of bromine is different from that of magnesium. Suggest why magnesium is a liquid over a much greater temperature range compared to bromine. Bonding is something I can guarantee you will come up in the summer exam. It's one of the topics that you will not be able to solve the questions on unless you have a good and clear understanding of the different types of bonding and how they occur. So if you've not got that, you need to make sure you go back and you learn that. So the first thing we need to do is explain that bromine is a simple molecule. And that means that its atoms are held together by strong covalent bonds. But the molecules are only held together by weak intermolecular forces called van der Waals. So that means it's going to have a relatively weak melting and boiling point. If we compare it to magnesium, magnesium is a metal. So magnesium ions have a strong electrostatic attraction to delocalized electrons. Then you want to say something like more energy is needed to break or overcome metallic bonds compared to van der Waals forces. And that explains why magnesium has a much higher melting and boiling point. In terms of the liquid range, magnesium has a much greater liquid range because forces of attraction in the liquid are stronger than they would be in bromine. The bromine, the van der Waals forces, once you overcome them, it doesn't take much energy to go from a solid to a liquid and then into a gas. So once you've started to put enough energy in to overcome those van der Waals forces, it doesn't take much energy to break them all. So if we put something to that effect in. Okay, so in terms of the marks, you're going to get 1 mark for identifying that bromine is a simple molecule. And you're going to get a 2nd mark for saying that magnesium is a metal. But they want some reference to the bonding for that one. You get a 3rd mark for talking about how bromine molecules are held together by weak intermolecular forces. You get another mark for saying that metallic bonds are going to be stronger than the intermolecular forces. And then a 5th mark for explaining the liquid range. Figure 2 represents 2 glass flasks, P and Q, connected via a tap. Flask Q has a volume of 1 × 10⁻³ centimetres cubed and is filled with ammonia. So that's this one, and we know it's filled with ammonia. So I'm going to draw my colour in to show it's filled. And we know the ammonia in there is at 102 kilopascals and 300 Kelvin. The tap is closed and there is a vacuum in flask P. Okay, we also know the volume of this flask here is 1 times 10 to the 3 centimetres cubed. Okay, so that's the information we've been given in the question. Sometimes if you annotate the diagram, it can make it a little bit easier to see where the question's going. So we need to calculate the mass of ammonia in flask Q. Okay, well, to do that, we're going to have to work out the moles. So we're going to have to use the ideal gas equation. So the ideal gas equation is PV equals nRT, and we need to rearrange it to get N equals PV over RT. Be careful substituting your numbers in. Make sure you're putting them in the right units. The biggest mistake that are made with ideal gas equation questions are people don't convert the units. So pressure needs to be in pascals. So to go from kilopascals to pascals, you times by 1,000. Volume needs to be in meters cubed. So to do that, we divide by 1,000,000. So if I divide this by 1,000,000, it becomes 1.0 times 10 to the minus 3. R is just the gas constant, so we can put that straight in. And temperature has to be in Kelvin, and the temperature is given to you in Kelvin, so you don't have to convert that. Now, if you calculate that, the number of moles will turn out to be 4.09 times 10 to the minus 2. Now I've got the number of moles, I can now work out the mass. So moles equals mass over mR. So mass is going to be moles times mR. It doesn't actually give you the formula of ammonia, but you should know ammonia is NH3. So its mR is going to be 17. So that gives us an answer of 0.696. Now we've got to do it to the appropriate number of significant figures. So let's just go back to the question and have a look at all of the values that are used. So we've got one here that's to 3 significant figures, that's to 3 significant figures, that's to 3 significant figures, that's to 3 significant figures. So our answer should be to 3 significant figures. You always go with the one that's got the lowest precision. So if you had 3 of them to 3 sig figs, but only 1 to 2 sig figs, then you would have to go with 2 sig figs. But all of them have got 3 sig figs with this one, so we're going to stick with 3 sig figs. So there's our answer. When the tap is opened, ammonia passes into flask P. The temperature decreases by 5 degrees C, and the final pressure in both flasks is 75 kilopascals. And we need to calculate the volume. So let's see what information we've got. If we know it's a volume, we know we're going to be using the ideal gas equation again. So we want to rearrange it for volume. So it's going to be nRT over P. Now, N is the number of moles. We've not added or taken any ammonia away from this. So N is going to be the same as it was in the previous question. 4.09 times 10 to the minus 2. R is the gas constant, which will be 8.31. T, well, we know temperature originally was 300 Kelvin, and we've had a 5 degree drop. And remember, 1 degree Kelvin is, in the change in temperature of 1 degree Kelvin is the same as the change in 1 degree C. So that gives us 295 Kelvin. And pressure is given to you in kilopascals. Remember, you've got to convert it. So that becomes 75,000 pascals. The next thing we need to do is substitute that into the equation. And that comes up with a value of V, which is 1.34 times 10 to the minus 3. Now remember, it comes out of the ideal gas equation as metres cubed. Now we've worked out the total volume, so that means we've worked out the volume of both of those things added together, so all of this. We just want to work out the volume of part of it. We just want to work out the volume of P. So if we've got the total volume and we take away the volume of Q, we're going to get the volume of just P. So the total volume we've just worked out. The volume of Q was given to you in the previous part of the question as being 1.00 times 10 to the minus 3. So if we take one away from the other, we get our volume of P being 3.42 times 10 to the minus 4. Now remember, this is still in metres cubed. This asks us for the answer in centimetres cubed. So what we need to do to convert it into centimetres cubed is to multiply it by 1,000,000, which comes out as 342 centimetres cubed. So that gets us 1 mark. For doing this, realising that was the total volume and subtracting the volume of Q, you get another mark. And the other mark was for correctly putting the numbers into that equation and getting the right answer. If you put the numbers in correctly and somehow managed to get the wrong answer, you would still get that mark. Explain how ions are accelerated, detected, and have their abundance determined in the time of flight mass spectrometer. It's really important you read the question thoroughly. The amount of papers that were marked that went through descriptions of how things were ionised and talked about the free drift and separation. The question isn't asking you that. It's asking you specifically how things are accelerated, detected, and how they have their abundance determined. So, accelerated. Now that's by the ions being attracted to a negatively charged plate, or you could say they are accelerated by an electric field. I think I'd probably go for the electric field just because it takes less effort to write. We don't need to write anything about free drift or anything like that. We need to know how they're detected. And they're detected by gaining an electron. So they hit the plate and they gain an electron. And the abundance, when they hit the plate and they gain an electron, they cause a current. And the current is proportional to the abundance. Calculate the mass in kilograms of a single 52 chromium ion. Assume that the mass of a 52 chromium ion is the same as that of a 52 chromium atom. So we're negating the mass of an electron, which is fairly tiny anyway. So to be able to do this, we need to work out the mass, which is going to be the mass of the ion in kilograms divided by Avogadro's number. So it would be 52 divided by 1,000, because that would be the mass of 1 mole. Remember, the masses on the periodic table would be in grams. And then we need to divide that by Avogadro's number, which is 6.22 times 10 to the 23. Which gives us a mass of 8.6 I've only really got 2 sig figs, so I'm just going to put 8.6 times 10 to the minus 26. In a time-of-flight mass spectrometer, the kinetic energy of the 52 chromium plus ion was 1.269 times 10 to the minus 13 joules. Calculate the velocity of the ion using the equation. Okay, so we want to rearrange that for velocity. So it's going to be the square root of 2 times the kinetic energy divided by the mass. So 2 times the kinetic energy is given to us in the question. And the mass is the answer from the first bit. If you got the first bit wrong, but you correctly used your mass and you showed the calculation clearly, then you will have got full marks for this. Don't forget to put the units, which is metres per second. Pretty quick, but you'd expect a subatomic particle to be flying pretty quickly through a mass spectrometer. So that's a sensible. If you get very slow speed, something's probably gone wrong. So that seems quite sensible. Now you get 1 for correctly rearranging it and putting the numbers in, and a second one for correctly calculating the answer. Bromine has 2 isotopes, 79 and 81. In approximately equal abundance. In a time-of-flight mass spectrometer, bromine forms ions with the formula Br2. Sketch the patterns of peaks you would expect to see from the mass spectrometer in a sample of bromine. Now, there's probably nice statistical ways of doing this, but this is the way I would think about it. So we've got 2 of those isotopes. Let's have a look at the ways they could combine. So we could have 79 and 79. Which would give us a peak at 158. Okay, then we've got 81 and 81, which would give us a peak at 162. I'm just adding the 2 together. And then I could have 79 and 81, which would give me a peak at 160. And there's a second way that can combine. So this one is twice as likely to occur as either of these 2. Now my total abundance can only be 100. This one's going to appear half of the time. So that means my peak at 158 should be 25 of it. My peak at 160 is 50. And my peak at 162 is going to be 25. Because 25 plus 25 plus 50 make 100%. I know this middle peak is going to occur 2 ways, so it's going to be twice as common than the other 2. There are 2 marks for this question. The first mark is for identifying where the peaks will be, and the second mark is for getting the ratios correctly, so the 25 to 50 to 25. A sample of xenon has a relative atomic mass of 131.31. The sample consists of 4 isotopes. The abundances of 3 of the isotopes are shown in table 3. The data for one of the isotopes is missing. Okay, and that's said it's M. Use the data to calculate the abundance of the unknown isotope. Okay, so we know that the total relative atomic mass is 131.31. And that would be equal to the MZ value times the abundance for each isotope. Now the last one we don't know the value of. So we're going to call it MXE. But we do know its percentage. So the percentage of MXE is going to be 100 minus 28.0 plus 25.0 plus 27.0 because it has to add up to 100. So if we work that one out, it comes out as 20%. So we know that one is multiplied by 20. Now don't forget, these are all percentages, so it should be over 100. Now you get 1 mark for just working out that missing percentage, as long as it's clear what it is. You get a 2nd mark for writing this equation out with the unknown in it. You get a 3rd mark for expanding those brackets so it looks like something sensible. So if I work all those numbers out and take them over to the other side, they become a negative, and it's 104.51, and that's going to be equal to 0.2 XE. 0.2 because it's 20 divided by 100. We've divided everything by 100 as well. So you'd get a mark for showing you're resolving it. Now if I resolve that by bringing the 0.2 to the other side and taking 104.51 from 131.31, it gives me a mass number of 134. Now it's got to be appropriate precision. Everything in the question has been given to, we've got one that's to 5 sig figs there, but everything else is only to 3. So our answer should only be to 3 sig figs. And these are also isotopes, and you can't have an isotope that's point something, so it's got to be a whole number. So if you don't do that to a whole number, which is an integer, you're going to lose a mark. Ammonia reacts with aluminium chloride as shown in the equation. Draw diagrams to illustrate the shapes of NH3 molecules and AlCl3 molecules. Okay, so let's have a look at nitrogen. Nitrogen is in group 5. So it has 5 electrons in its outer shell. 3 of those are going to form covalent bonds with hydrogens. So we can see it's got 1 lone pair and 3 bonding pairs. So that means it's going to be based on tetrahedral. So we'll put the lone pair in at the top, and the other 3 bonds, make sure they're all pointing downwards. Think about your shape for tetrahedral. Because one of them's a lone pair, we actually call it pyramidal. If it was tetrahedral, the bond angle would be 109.5, but that lone pair is going to reduce it. So the bond angle, make sure you indicate it's between 2 of the bonds, is going to be about 107 degrees. If we have a look at the other one, aluminium is in group 3. So it has 3 electrons in its outer shell. It's going to form 3 covalent bonds with chlorine. So this time we have no lone pairs and we have 3 bonding pairs. 3 bonding pairs is going to give us a trigonal planar shape. So these chlorines are going to get as far away from each other as they can, which gives us a bond angle of 120 degrees. Now the way the mark scheme works for this one is you get 1 mark for showing the structure of ammonia, including the lone pair, 1 mark for the structure of aluminium chloride, and then 1 mark if you get both bond angles. Now they're quite nice with the bond angle for ammonia. They will allow you to have anything between 106 and 108 because the bond angle for each lone pair is reduced by about 2 degrees. It's not exactly 2 degrees, so there's a little bit of scope. The other one has to be 120. Name the type of bond formed between the N and the aluminium, the nitrogen and the aluminium in that molecule, and explain how this bond is formed. So if you didn't get your structures right, this is going to be a little bit tricky. So we know we've got ammonia with a lone pair there, and we've got aluminium with only 3 pairs of electrons in its outer shell. So this is going to form a dative covalent bond. So the type of bond is going to be a dative covalent, or we can call it a coordinate bond. They are the same thing, and it doesn't matter which one you use. The explanation, well, it's a covalent bond, so we've got a shared pair of electrons, but we want to say that the shared pair of electrons come from the nitrogen. So we'd get 1 mark for each. Explain how the value of the CAlC bond angle in AlCl3 changes, if at all, on the formation of this new compound. So aluminium has gone from having just 3 bonds or 3 pairs of electrons to having 4. So it's gone from being a trigonal planar shape to a tetrahedral shape. Well, in trigonal planar we've got 120 degrees, in tetrahedral we've got 109.5. So we're going to get a reduction in the bond angle. Okay, and if you've identified that the bond angle is going to be reduced, then you're going to get a mark. You need to justify why, so you'd say aluminium now surrounded by 4 bonding pairs, therefore bond angle reduced from 120 degrees to 109.5 degrees. A student was given a powder made from a mixture of anhydrous. Now anhydrous means without water. It's anhydrous barium chloride and anhydrous magnesium chloride. The student dissolved 1.056 grams of the powder in water in a conical flask and added an excess of sulfuric acid to make sure all of the barium ions had reacted. A white precipitate of barium sulfate formed and was filtered off, washed and dried. It was found to weigh 0.764 grams. Write a balanced equation for the reaction between barium chloride and sulfuric acid. So let's start with that. So barium chloride, barium is in group 2, so it's got a 2+ charge. Chlorine is group 7, so it has a -1 charge. So to balance it, we're going to need 2 chlorines for every barium. You should know the formula for sulfuric acid. If you don't, you need to learn it. And we know that we're making barium sulfate. Barium has a 2+ charge. The sulfate ion has a 2- charge. So they just go together. And we're also going to form hydrogen chloride, because we've got the hydrogen from the acid and we've got the chlorine left over. Now I've got to make sure that's balanced. The bariums are balanced, the chlorines aren't. Let's put a 2 there. Hydrogens are now balanced and the sulfates are now balanced. So we have a balanced equation. The next bit asks us to calculate the percentage by mass of magnesium chloride in the original powder. So we need to work out how many moles of barium we had, or barium sulfate we had at the end. And we can do that by doing mass over MR. The dry weight was 0.764, and using the periodic table we can work out the MR of barium sulfate at 233.4. Remember, when you're working out an MR from the periodic table, always do it to 1 decimal place. And that gives us 0.00327 moles. Okay, from the equation, 1 mole of this comes from 1 mole of that. So this is also going to be equal to the moles of barium chloride. So we can now work out the mass of barium chloride in the original sample. And that's going to be moles times MR. The moles we've just worked out. And the MR of barium chloride, if you use the periodic table to calculate, is 208.3, which gives us a mass of 0.6818 grams. So we're trying to work out the mass of magnesium chloride by a percentage. Okay, so to work out the mass of magnesium chloride, we're going to take the original mass, we're going to take away the mass of the barium chloride, which we've worked out, and we want it as a percentage of the original. Well, that's the original mass, and then we're going to times it by 100. And that should give you a 35.4% mass. In terms of precision, we've got things to 3 significant figures. 1 to 4, 1 to 3. So our final answer should be to 3 significant figures. Now you get 1 for calculating the percentage. You get 1 for working out the mass of barium chloride. And you get 1 for working out the moles of barium sulfate.